Hello, everyone. Let's start. My name is Timur. I'm a C++ developer. I'm also a member of the C++ Standard Committee, and I'm also one of the people behind Include CPP. You might have heard about it. If you want to know what we do, come speak to me afterwards. I'm going to talk to you today about initialization in C++, which seems like, well, it's a very basic thing, right? But turns out it's actually not that easy in C++. So I'm not sure if you've seen this particular GIF here, which I found at some point on the internet. And I think that's pretty much the summary of my talk today. Yeah. So this is pretty much true. I think, so I retweeted this on Twitter when I found it, and there was some discussion. And one of the first comments was, yes, so this is great, but the person who made this GIF failed to mention these other 3 types of initialization, which are not in there. So it's actually missing some stuff. And then there was quite a long discussion, and then at some point someone suggested I should maybe do a talk about these things. And yep, so now I'm doing a talk. So I find it very interesting, why I wanted to do this talk is because I find it very fascinating that something as basic as initializing a variable can be so complicated. I think it's a remarkable property for a programming language. It's probably a unique property. Like in most languages I know, it's pretty easy. In C++ it's not. There's probably no other area, or not very few other areas in the C++ language where over the years there's been so many defect reports and complaints, it doesn't quite work, and then in the next standard we kind of change the rules again, and then we change the rules again, and then so there's for example, this other talk by Nico from last year's CPPCon, where he came up with 19 different ways of initializing an int. Yeah? Imagine that. And then there's all these blog posts on the internet saying how initialization in C++ is bonkers. So this seems to be a very complicated topic, even though initialization is so basic. So giving a talk about this and trying to give some kind of systematic overview is an interesting challenge. But I'll try to do it anyway. So what we're going to discuss today is different ways to initialize an object in C++. And I'm going to do this chronologically. So what are the things we kind of inherited from C? What are the things that were introduced in the first version of C++, and then what were the new things as you went through the history of C++ and introduced C++ 03, 11, 14, 17, and basically all the different types of initialization that were introduced, and what they do, what the pitfalls are, some recommendations, how to use them properly, and also, at the end, if we have time, what's new actually in C++ 20, because C++ 20 introduces yet more things related to initialization. And at the end, there's going to be an overview table. All right, so let's start. Of course, C++ has inherited a lot of stuff from C, so we need to start with C, and we need to start to look at what are the different ways to initialize a variable in C. Turns out in C, well, the most basic thing is to just not initialize it at all. Right? So you just have an int, and you just don't initialize it. And that's called, irritatingly, default initialization in C++. So whenever you don't initialize something, that's called default initialization. I think it's very misleading, because you might think, well, then it's initialized with some kind of default value, which is totally not what's going on. Right? So it's not initialized at all, which means that if you access that value, which is not initialized, you get undefined behavior. Right? So I think calling this default initialization is a bad name for it, but this is what the standard calls it. So default initialization means if you don't initialize it, then accessing a value that hasn't been initialized is undefined behavior. And that is something that has been like that always in C. And also, it's not just for ints, but in C, if you have a struct and you don't initialize the members, you get the same thing, right? So this has been like that for many decades. And if you then switch from C to C++ and you have classes, turns out it's the same thing, right? So if you have a class, a C++ class, you get all these fancy stuff. You get public and private, and you get member functions. And but if you still have, in this case, private members, or no matter public, private, members in this class, and you don't initialize them, and then you try to access them, like here you access them through this getI function, turns out that it's still undefined behavior, right? Because all this fancy stuff with like constructors and classes and things, it doesn't somehow magically initialize these members. You still have to initialize them, just the way you have to do it in C. So which means that this program is also undefined behavior. And interestingly, for the first couple years of my own career as a C++ developer, I did not know this, right? So I would write code like this. My compiler wouldn't tell me, oh, you forgot to initialize member I. My IDE wouldn't tell me. Now I use an IDE that does tell me. But back then, in a code review, my colleagues wouldn't find this bug either. So I would probably introduce some weird bugs in production code at some point, because I did not know that C++ classes don't initialize their members by default. So I think this is interesting. Of course, if you then know about this, then there's several ways to prevent this. So in C++ 98, we have this member initializer list where you have to explicitly initialize the members. You can do it with this syntax. It's a bit dangerous because you have to repeat it in every constructor, so it's easy to miss one. And then actually the order in which you write those is not the order in which they're initialized, but the order in which they're initialized is the order in which you declared them. So it's pretty confusing. So since C++ 11, we have a better alternative. We have default member initializers, where if you declare the members, you can initialize them right there, and you do it once, and then all the constructors will just use this. And I think that's a much better way of doing it. And I need to stress this, that the recommendation is to just always use direct member initializers. So this is what I do when I write classes. When I have members, I always put a DMI on them, just because it kind of forces me to think about that, right? So. For example, here, if you have like a float member, obviously you initialize it to 0. If you have an object, then maybe it has a default constructor, maybe it's doing the right thing, but still worth writing it out. And for example, if you have an atomic member, then actually the default constructor does not initialize the value. So for still atomic, you have to actually initialize the value explicitly to 0 or whatever you want. Not everyone remembers this, but if you have this kind of habit of always writing a default member initializer, then it kind of forces you to think about that. Oh, but yeah, how do I initialize this member correctly? So it's kind of this extra step which kind of sometimes prevents bugs. So I think it's a good practice to always use direct member initializers. All right, so we have default initialization, right, which is the first type of initialization we inherited from C. The next one is copy initialization. And copy initialization is what you get when you write type variable equals value. So whenever you write an equal sign, you get copy initialization. The other two scenarios where you get copy initialization, if you pass an argument into a function by value, like this I, or if you return something by value. It's like return I times Y. So all of these three things are copy initialization. So again, copy initialization, whenever you initialize something with equals, or when you pass by value, or when you return by value. And this equals syntax is also maybe a bit confusing because it looks like it's an assignment, but it's actually not an assignment, right? So it's initialization, because you call a constructor or you initialize the value. So it's not an assignment. There's no assignment operators. Nothing in this talk talks about assignments. This is a talk about initialization. So remember, it's not an assignment. It's initialization. And so the other thing about copy initialization is that if the types don't match, copy initialization performs something that we call a conversion sequence, right? So if you write int I equals false, for example, then that's a bool. You're initializing an int. So there's all these rules in the standard how this conversion sequence tries to convert the type you have to the type you need. And one of those rules is that if you have your own class and it has constructors, explicit constructors are not converting constructors. Explicit constructors, they do not participate in a conversion sequence, which means if you do this, that's an error, right? So you try to initialize the widget with an int. You have a constructor that takes an int, but because you're using copy initialization equals some int, that's going to do a copy conversion sequence. Conversion sequence is not allowed to call an explicit constructor because that's not a converting constructor, so you get an error. More interestingly, if you have another constructor which is not explicit, it's going to call that, right? So you're trying to copy initialize with an int, the explicit constructor is not considered, and then you're going to end up calling the other constructor, which takes a double. So you get another conversion, which is probably not what you expect, but this is how copy initialization works. Right, so now we have default initialization and copy initialization. The next thing that we also inherited from C is aggregate initialization, right? So aggregate initialization means if you have an array, you can initialize it with equals braces and then a list of initializers. And this also works if this has a few nice properties. So for example, it does array size deduction. So if you don't write the size of the array, it's going to deduce it for you from how many initializers you wrote, right? If you wrote 4 ints, it's going to initialize an array of 4 ints. So that's called array size deduction. And it works not just for arrays, but also for structs. So if you have a struct in C, like any struct, or in C++, aggregate, you have an aggregate class, which means it has no private members, it has no virtual functions, and a few other conditions. So basically, whenever it's a class that's just a bag of values, you can use aggregate initialization. And that's just going to, member-wise initialize it. So this equals brace syntax has been with us since C and since C++98. So this has worked always. Since C++11, we get this additional syntax where we can just use the braces without the equals sign. We're going to talk about that a lot more in later parts of the talk. So yeah, but that has been with us since a long time. Important things to keep in mind. What does aggregate initialization actually do? It copy initializes the elements, right? So if you look at then, again, at this example, how copy initialization works, again, if you have this explicit constructor, you're not going to be able to use copy initialization with int. So if you try to aggregate initialize this thingy, which has widgets inside, so aggregate initializing the thingy means you're going to copy initialize the elements of the thingy. So you're going to try to copy initialize the widgets with ints. That's not going to compile because that one is explicit. So I think this is all kind of basic stuff, but if there's any questions, please feel free to kind of raise your hand and interrupt. Right, so aggregate initialization. And if you have this other constructor, then again, it's the same as before. Aggregate initialization copy initializes the elements, so it's going to call the double constructor. Another interesting property of aggregate initialization is that if you don't write all the initializers, it's going to do 0 initialization for the ones that you didn't write. So what does this program return? Can someone tell me what this program will return? 0. Yes, 0. Because you have 2 elements, but you only initialize 1, so the other one will get 0 initialized, which means this is fine. This is going to return 0. Right. And that's really useful. For example, you can do this where you have a long array and you can just write brace and it's going to 0 initialize all the elements. It's a very quick and useful way to kind of quickly 0 out some memory. The other thing so aggregate initialization has this special feature that it 0 initializes things you didn't write, and the other special feature that it has is brace elision. So next quiz question. What does this program return? Someone knows? Okay, someone said 2, someone else said 0. Okay, who thinks it's 2? Who thinks it's 0? A few more people. Yeah, you're good. Yeah, of course it returns 0. Why? So this is a case where you have sub-aggregates. So this whole aggregate initialization thing nests, right? So you have the thingy, which has a widget and an int, so it has 2 elements, but the widget itself is also an aggregate with 2 elements. So you can kind of, it's going to recurse into the sub-aggregates and initialize the elements of the sub-aggregates. And then brace elision means that if you do this, you're allowed to omit the nested braces, which means that if you write 2 elements, it's not going to initialize the 2 elements of the thingy, but instead it's going to recurse into the widget, initialize the 2 elements of the widget, and then the k is going to be, you didn't write an initializer, so it's going to be initialized to 0. So this returns 0. So this is brace elision, which works with aggregate initialization. It's really important. Right, it has one more thing we inherited from C, which is static initialization. Yes. Yes. So, so the question is, if you want to initialize k, you can write it out with the nested braces, like in the comment, but you can also just omit the braces. You can write a list 1, 2, 0, just flat list. You can do that. That's exactly what brace elision is. So the comment was, yes, it would be safe. Of course, it's dangerous. That's kind of the whole point, right? So don't do this. But remember that the compiler will do it for you. If you forget to write the nested braces, it's just going to assume that that's fine. It's going to recurse into the sub-aggregates. Sorry?
Are there flags in some compilers to disable this feature?
I'm not aware of any flags in any compilers to disable this. This is just the way the syntax works. So just remember this.
For me, it's no problem.
Yeah. So it's weird, right? Because thingy has 2 elements, but then if you write 3 elements, just 1, 2, 0, or 1, 2, 3, then that's what you actually need to do if you want to initialize all of them. But one very important property that I didn't mention is, if you omit something, it's going to 0 initialize it. It means it's going to be initialized, which means that if you're using aggregate initialization, even if you got this wrong, you will never end up with things that are not initialized. That's very, very important to remember that in this case, actually, aggregate initialization is safer. Because whenever you use these braces with aggregate types, sometimes you can run into things where like it doesn't initialize it the way you thought, but it's always going to be initialized. So you're never going to run into undefined behavior. So that's actually a good property. Right. Static initialization. Right. So if you have a static variable, you initialize it with a constant, you get constant initialization, which means basically it's going to initialize it at compile time. If you omit the initializer, now for static variables, that's different, right? Static variables will always be initialized, which means that if you don't initialize them, they're going to be 0 initialized by default. So that's different from non-static variables. So which means that this function actually is fine. You didn't initialize j, but it's still going to return 3. That's defined behavior because it's been initialized to 0. There's this thing called initialization order fiasco. I'm sure you've all heard about this, where if you have static objects and you initialize them, then well, so that's fine, but I was working once with a framework where you had these kind of static colors predefined, like red, green, blue, etc., etc. And then in another place, there would be another static object initialized with some of these colors. And then basically, if they're in different translation units, then the order in which static variables are initialized is undefined. So you're probably going to crash your program if you do this. But, of course, if the constructor is const expr, then you get constant initialization. Constant initialization is guaranteed to take place at compile time, essentially, which means that if you have a const expr constructor and the thing you're initializing it with is a constant expression, then you're fine. That's not going to happen. So, which is why it's good to have const expr constructors, because then you get constant initialization, which is safe. Yes?
Put that in a function, right? Leave it as static, but in a function, then it will be okay, because it will be initialized the first time the function enters.
Yes, but then you cannot, so the comment was if you do that inside a function, then it's going to be initialized whenever the function is called. Yes, but then you can't use it outside. But you want to access this thing outside probably, right? So it's just a different feature then, different use case. Anyway, so we're done with the stuff that we inherited from C, right? So we have default initialization, you have copy initialization, you have aggregate initialization, which has some special properties, and we have static initialization, right? So this is already quite a lot of stuff, and this is all just from C. Comment in the back? Yeah, yes, so zero initialization in itself is also another type of initialization, but it doesn't have its own syntax, but it happens in certain cases, right? So if you aggregate initialize, then the members for which you didn't write initializers are going to be 0 initialized, and then also if you have a static variable and you didn't write initializer, it's also going to be 0 initialized. Zero initialized means that, yes, so if it's like a int or a float or something, it's going to be initialized to 0. If it's a class, we're going to come to that. Um, yes, if they're const expr. Okay, cool. So this is the stuff we have from C. But of course, we are C++. So when C++ was developed by Bjarne long time ago, what is the one feature which lets us initialize things in a different way which we don't have in C? Constructors, of course. So in C++ we can call constructors, and for this we have a new syntax which doesn't exist in C, which uses parentheses. And then, of course, to be consistent, you can use the same syntax in C++ to also initialize things that don't have constructors, like an int. So you can initialize any type with this syntax. And that's interesting because it creates like new syntaxes for things, which, it's just more interesting cases. And that way of initializing things is called direct initialization in C++. So whenever you have an initializer which is an argument list in parentheses, that's called direct initialization. And there's a few differences between direct initialization and copy initialization. So for built-in types, there's no difference. You can write int I 3, or you can write int I equals 3. That's going to be the same. For class types, there's a few differences. The first one, which is the obvious one, is of course direct initialization can take more than one argument, which is the reason why we need a new syntax for this in the first place, right? But then the other thing is that it actually does not perform the conversion sequence like copy initialization. It has different rules. What it does is it does overload resolution, so it behaves like a function call, which I think is actually intuitive, because if you're using parens, you're calling constructors, which are essentially functions. So what you're doing there is you're using overload resolution rules, like for normal functions. And that's going to decide which constructor is going to be called. So if we look again at this class where we had this constructor, so if you do copy initialization, it's going to give you an error, right? We covered that. If you do direct initialization, it's fine, because it's just using overload resolution. So it's going to be, okay, you're giving me an int, there's a constructor taking an int, doesn't care about the explicit, it's going to call that constructor. So in this case, direct initialization and copy initialization are giving us different results here. And it's getting even more interesting if we add this other constructor. Then it turns out both compile, but they call different constructors, right? So w1 equals 1 will call the double constructor and convert the int to double, because it can't call the explicit one, because it's not converting. Direct initialization will just do overload resolution. It will say, okay, well, I have one function taking an int, another function taking a double. You've given me an int, so the int is a better match. You're done, right? So this is really easy to reason about. It works just the same way as for other functions. And direct initialization is whenever you have parens. So it's not just when you call a constructor like this, but also when you create like a temporary. You just write like type name and then in parens. It's the same if you write a new expression and you give the new object arguments in parens. In a cast expression, you also have parens. So that's really easy to remember. Whenever you have parens, you have direct initialization. There's one problem with direct initialization, which has been with us since this was invented, since C++ exists. Does anyone know what that is? What's the problem with this syntax? What? Yes, there's a bigger problem, which is the most vexing part. Huh? Oh, yeah. Like in what order the arguments are being evaluated. That's a completely different problem. Yes, that's also a problem. But it's not related to initialization, right? Because that's the same for any kind of function call. Right, but the problem, of course, specifically with initializing an object with the syntax is the most vexing part. So let's say you have a class widget and a class thingy that takes a widget. And what you want to do in this case is you want to initialize your thingy by just giving it a kind of a temporary default constructed widget. So you say, okay, I want a thingy, and I'm going to give it widget paren, and that's going to be like a temporary object, and I'm going to use that as an initializer to call the constructor. Unfortunately, if you write that line there, it's going to compile, but it's not going to do what you want. It's going to be a function declaration, right? So this actually declares a function that takes a function that takes nothing and returns a widget and then returns a thing. right? So you're declaring a function that takes a function. And you can run into this in actual code. Like there's some cases, like for example, with where you create like stream iterators and pass them into functions. And there's different cases where you actually hit this problem in practice and it compiles. And then later when you try to do something with the object that you initialize, it turns out it has the wrong type, it's a function, and you get really weird compiler errors. So this is a problem. There's ways to dealing with that, which we will talk about. But yeah, so this is where we are in C++ 98. So we have all the stuff from C, and then we also have this new thing which is called direct initialization. And it has this problem. Okay, we're good so far? Cool. So what's the next standard after C++ 98? 03. And someone mentioned yesterday, oh yeah, but 03 was like just a minor bug fix release. Most people think that. That's actually not true. C++ 03 introduced a pretty big feature. Can someone name a feature that C++ 03 introduced? No, auto was introduced in 11. So C++ 03 introduced a new way of initializing things. It's called value initialization. And that's what happens when you have paren with nothing inside. What is this program going to do? Return 0. So in C++ 98, this is undefined behavior. Because you're not initializing the int, you're accessing its value. In C++ 03, that's okay. Because that's going to be value initialization. So basically, whenever you have paren with nothing inside, you're going to get value initialization. It's the same if you write like a new expression, like new widget paren. That's also value initialization. And what does it do? Well, if the type has a user-provided default constructor, then it's going to call that default constructor. Otherwise, you get 0 initialization. So that's the other case where you get 0 initialization. So coming back to this program, int paren is value initialization. Int is not a class type. So then it's going to do 0 initialize it. So that's just return 0. Right. So this user-provided default constructor, turns out, is not quite as easy as you think. So what does it mean if you have a user-provided default constructor? That's actually very interesting. So let's look at this program. What is this going to do? So we just found out that paren is going to do value initialization. Value initialization is going to 0 initialize things if they don't have a constructor. What do you say? It returns 0, yes. Since C++ 03, right? So widget paren is going to do value initialization, and that's going to do 0 initialization. So the I is going to be 0 initialized, right? So 0 initializes everything in widget. Now, that's going to happen. Again, value initialization is going to do 0 initialization if you don't have a user-provided default constructor. What happens if we add a default constructor? We don't change anything else. We just provide a constructor. Well, now our program is undefined behavior, right? We only added this constructor, but now you don't get 0 initialization anymore. Instead, value initialization is going to call this constructor. The constructor is not initializing the I, because you forgot to write a direct member initializer. You get undefined behavior. It's uninitialized. Now, what does it mean if you have a user-provided default constructor? So this is C++ 98 code, right? Widget paren, brace. In modern C++, we don't do brace anymore. We have a better syntax to declare something which is like a trivial default constructor. You just write equals default. Turns out, if you write equals default, it's not user-provided anymore, right? Because you didn't write the body of the constructor. So if you write brace, that's a user-provided default constructor. If you write equals default, that's a user-defined default constructor, but it's not a user-provided default constructor because you did not provide the body of the constructor. So just changing curly to equals default is changing it now from undefined behavior to value initialization again. To 0 initialization.
So the question,
If you provide default value for I, you're fine. It's always going to be initialized. This is why you always should provide default values, because then it never can be uninitialized. Well, if you do provide a direct member initializer, then yeah, it's not going to be initialized to 0, it's going to be initialized to whatever you wrote there, yes. It's kind of the obvious thing, right? Okay. But now we are not done yet, because it turns out that if you just take this widget parent equals default and move it outside of the class, right? You just define it out of line. That's undefined behavior again. So that's a really nasty trap here. So if you provide the body, it's going to get called. If you write equals default, you get 0 initialization because it's not the user provided default constructor. But if you do this equals default out of line, outside the class, then it again counts as user provided, and then you get undefined behavior again. And that actually makes kind of sense, because if you do the equals default outside of the class, you might be doing it in another translation unit. So the compiler wouldn't see that you write equals default. So if you write equals default outside of the class, it's going to treat it as if you wrote like an actual body, because it doesn't know. It might not know. Maybe you did that in this other translation unit. It can't assume that you wrote equals default somewhere else where it can't see it. So if you don't have equals default inside the class, it's going to assume it's a user-provided constructor. It's going to count as a user-provided constructor. Okay. Yeah. So this is what we get in C++03. Value initialization either performs, like, calls the default constructor or does 0 initialization, depending on these rules. Problem as well, of course, most vexing parts, right? So if you write widget paren, that can be a function signature. Right. So this is what we have in C++98 and C++03, and now we come to C++11. And C++11 introduces this thing which we call uniform initialization, or I call it unicorn initialization, because it's this thing that just magically solves everything. So unicorn initialization, right? So what does it do? Why does it exist? So when the committee was working on C++11, they tried to solve these problems, right? So we have too many different syntaxes for initializing objects. We have this vexing parse when we use parens. And then the other annoying thing is that we can do aggregate initialization with arrays, but we cannot do it with other array-like things, like a vector. So with a vector, you can't initialize it like this. You instead, in C++98, have to write this kind of long reserve pushback stuff. So we want a way to kind of customize this, like being able to use this brace syntax with user-defined custom types. So the idea is kind of, okay, so how do you fix this? Oh, yeah, of course, by introducing yet another syntax for initializing things. This is the new syntax in C++98. It's called initialization, and the idea is kind of, it's one syntax for everything, right? So whenever you write these braces, it's just going to do the right thing depending on what kind of type it is. And because it's a new syntax, it doesn't collide with any other syntax, so you also don't have the vexing parse problem. To be a bit more exact, there's like 2 flavors. There's the new syntax, which is just the braces, which is called direct list initialization. And then there's the old syntax with equals brace, which is called now copy list initialization. Right, so it's a bit like with direct initialization and copy initialization, where you either have an equal sign or you don't. Now it's the same with list initialization. So whenever you have an equal sign, you get copy list initialization. And the thing in braces is now called a braced init list. And that is not really an object. It doesn't really have a type. It's like this special weird kind of thing. But it has one magic property that, okay, so if you have an aggregate type or a C like array, then you get, of course, whatever it did before. But if you then have a class, like a new kind of class, then this brace init list has this magic property. Like how do you make this work? You make it work by allowing this brace init list to implicitly convert to a std initializer list, which is this new type in C++11. So, which means that whenever you have one of those brace init lists, they're not really like an object, they don't really have a type, but if you have a constructor that takes a std initializer list, this thing implicitly converts to a std initializer list. So now it's going to get called. And there's a special language machinery to kind of do the thing. So this creates a few problems now. So I think this is where the committee maybe didn't quite find the right solution. Because, it's kind of good if you have the syntax, but this initializer list has a lot of problems with it. So first of all, it's a magic library container type, right? So it's actually a type, which means, so it's basically like a fixed-sized vector with const elements. That's more or less what it is. So it's a type, it's defined somewhere in a header, so you need to include that header in order to use it. It has its own begin and end member function, it has its own iterator type. If you call this, notionally, copy stuff around, because it's also not movable because it has const elements. So of course, like in practice, the compiler will just, optimize all of this stuff away, but still, like technically, like syntactically, you're like creating and copying actual objects. Excuse me. Which makes it quite a lot more complicated. And then the other thing is that the way it kind of decides whether to call a constructor is also different. So whenever you have a brace init list, it's going to always try to call a constructor that takes the initializer list, no matter what else is around. And that creates a few surprises. So there's this poll that Shafiq did on Twitter a while ago, where the question was, if you had a magic wand and you could go back in time and remove one feature from C++, basically what's the most hated feature of C++? And turns out the winner is initializer list because of all these problems. Another great talk by Jason Turner, who gave a wonderful talk yesterday. So he also has a 90-minute talk just about how initializer lists are broken. So if you want to learn more about the actual technical problems, watch this talk. It's great. Very technical, very interesting. We're just going to show a few examples. So this is probably the most famous one. I think some of you, or many of you might have seen this. If you initialize a vector with 2 integers, it does different things. If you have parens, like direct initialization, or if you have braces, right? So if you have parens, it's going to call the constructor that takes a value type and an integer. And the first one is going to be the value that all the elements should have, and the other one would be how many elements do you want? Right? So then you would get 3, the first one is how many elements you want, and the second one is the value that they all should have, right? So, yes, so if you write vector 3, 0, you're going to get a vector with 3 zeros in it. But if you write the brace syntax instead, it's going to call the initializer list constructor, and then you're going to get a vector with 2 integers, which are 3 and 0, right? So this is kind of it's unfortunate, but people teach this and you learn it, but there's actually even more nasty examples. So this is one of my favorites here. So you have now a string and you initialize it with an integer and a character. So if you do it with direct initialization, it's the same as with the vector, right? 48A, so you get a string with 48 A's in it. If you do the same with curly braces, what do you get then? Someone said undefined behavior. That's wrong. It's not undefined behavior. 0A, yes. So what's going on here is it says, oh, you have written curly braces, so I need to call an initializer list constructor. So I have one that takes 2 characters, or initialize a list of characters. So let's take this 48 and convert it to a character, and it happens that 48 is the ASCII code for the 0 character. So it's going to do this really, really weird conversion where it takes an integer and converts it to a char in order to be able to call the char initializer list constructor. Even though there is another constructor which is a perfect match, right? It literally takes an integer and a char, but it's not going to call that constructor. Instead, it's going to do this really weird conversion and call the initializer list constructor instead. So that's really weird. And keep in mind that if you have braces, it's going to try really, really hard to call an initializer list constructor. Here's another example. What does this return? So now we have templates. That's the other problem with initializer list. It doesn't really work well with templates. So now we have basically this template function that is going to do brace initialization inside. And you give it, what does this return? 1. Someone said 1. Any other ideas? 3. Right. So if you initialize a string with the number 3, you're going to get a string with the size 3. So this is returning 3. Because string does not have an initialized constructor that takes integers. But now if you change string to integer, it's not going to return 3 anymore, right? Now it's going to return 1, because now you're initializing a vector of ints, you give it an int. So now it's like, oh, now this is an element, now this is an initializer list. So now it's going to return 1. And then if you use float instead of string, I don't actually know. So this shows you that it's like really, really difficult to reason about list initialization inside of templates, because it just doesn't really work. And yeah, so there's other reasons why it doesn't work. Like, it's very unfortunate that, for example, you can't really use brace initialization for aggregate types. So for example, you cannot write a make unique function or like a perfect forwarding kind of function that works for aggregates, because then you would have to do the curly brace initialization inside the template. It just wouldn't work. So we have all these problems with list initialization. Right, again, so list initialization, whenever you have braces, for aggregate types, it's just going to do aggregate initialization, just like in C and C++98. If you have a built-in type, like int, it's going to do the same thing as if you didn't write the braces. It's also easy. If you have a class type, if you have braces, it's going to try really, really hard to call a constructor, takes an initializer list. Only if it cannot do that, then the curly braces will actually call a normal constructor. Except there is even more, one more exception, which is empty braces, and they're again special. So if you have empty braces, okay, so for aggregate types, you know, they're going to do the thing, so they're going to do aggregate initialization. You didn't write anything, so it's going to zero initialize everything. But for classes, empty brace is not necessarily actually going to call the initializers constructor. It's only going to call the initializer constructor if there is no default constructor. So in this case, you have a widget that has an initializer list constructor. But if you write brace brace, that's the special case. Empty braces are special. It's going to call the default constructor instead. And then if you don't have an initializer constructor and you don't have a default constructor and it's not an aggregate type, then it's going to do value initialization. So brace brace is going to value initialize it. And this is going to do what we discussed before, the same as paren paren, right? So in this case, if you have, and this is again the same thing with the user provided default constructor. So if you have a default constructor but it's not user provided because you wrote equals default, you're going to get zero initialization. So if you write brace brace, that's fine. It's going to initialize I to 0. If you write the body, then it's a user provided default constructor, so then value initialization will actually not initialize the int, except if you, and so yeah, this is what we talked about before, same rules here, except that brace brace doesn't have the vexing pass problem, so that's better. The other thing is that list initialization does not allow narrowing conversions. So that's not going to compile, because inside a brace init list, you cannot convert double to an int. And actually, same here, like if you have a struct that takes 2 integers and you want to list initialize it, you give it some other type, which involves a narrowing conversion, like a conversion that might lose some precision or change the value, then that's not going to compile. And that's a breaking change in C++11. So that's the most common, you know, when people switched their compilers from C++98 to C++11, that was the most common breaking change. Since C++11, we cannot do narrowing conversions in list initialization anymore.
That's copy initialization, the last one, right?
The last one is copy list initialization, yes. But that was allowed in C++98. If you write the equal sign, that's allowed in C++98. But in C++98, you can also do conversions in there. In C++11, you cannot. So this is a breaking change.
The first one I understand because the initialization list is a template. It checks for the type. But the last one?
Yes, the last one is aggregate initialization. There's no initializer list constructors here.
So how does it check the type?
Well, how does it check the type? I mean, it's like any initializer. You have something on the right-hand side. The compiler has to figure out what the type is. It's going to see, okay, this is a list of doubles.
But usually it will convert it. Let's say it was the other way around. Let's say I entered integers and I was expected doubles. Then it would convert the data form automatically, right? Here no. But here no.
No. So what's going to happen? This is copy list initialization, which means the elements are going to be copy initialized. And then there's the special rule that if you have copy list initialization or any kind of list initialization, when you initialize the elements, you're not allowed to do narrowing conversions. And that's a new rule introduced in C++ 11. So now it's a consistent rule. Whenever you have braces, that's just the rule. And that was a change. Before, you could only use the braces for aggregate initialization specifically, and that didn't have that rule. Does that make sense? Okay, so that's a breaking change. Yes? Yeah, we started quite late. So we started like 10 minutes later. So can we do, should I talk faster? I'm going to try to talk faster. Yes?
With the state initializing list though, that you showed with the string, the 0A, there was an error conversion there. So with state initializing the list, is it allowed to do narrowing conversion?
No, that's not a narrowing conversion though, right? The conversion from int to char. Because int is because 48, like the compiler sees that 48 is, yeah, if you didn't write a literal, it wouldn't know that. But if you write a literal, it sees that 48 is fine. Anyway, I need to really speed up now because apparently we started late, but we can't overrun, so I need to speed up. Oh, yeah, so no narrowing conversion. The other thing is if you have initializers constructors, you don't get brace elision. So you have these kind of nested braces. So this is the good case, right? Where you have a map. The elements of the map are pairs, so you can list initialize every pair individually, like with a string and an integer, and then these pairs are then themselves the elements of the map. There is a case where this kind of nested brace stuff goes horribly wrong, which is this one. So if you have a vector of strings, you list initialize it with strings inside, it's fine. But if you add another pair of braces, what happens then? Anyone knows? Nothing? Okay. This is correct. So for list initialization, it doesn't, so you have to kind of work it from the outside to the inside, right? So the outermost braces means you have an initializer list. And then you go inside, then you have one other pair of braces, which means you're going to have one element in the list, right? So it's going to be one element, it's going to be that braced init list. And now it's going to try to initialize one string with a braced init list that has two string literals in it. And that's not going to concatenate them. There's a comma in between. So what's going to do is it's going to say, okay, we have two const char stars. We're trying to list initialize a string. Oh, well, a string has a constructor that takes a begin and end iterator to characters, right? So it's going to use that. So it's going to try to treat this as a range and like pointer to begin, pointer to end. It's going to try to read the ABC as a null terminated like range of, not null terminated, but as a range of characters with the end. So basically it's going to overrun into memory. It's not allowed to read and your program is going to crash, right? So this is just instant crash basically. And the other difference is that if it's not an aggregate, so you don't do aggregate initialization, but you do this kind of constructor stuff, then you don't get brace elision. Passing and returning brace init list is copy list initialization, right? So it's the same as with, so copy initialization is either if you write something equals value or if you pass it, if you return it. The same with brace init list. So if you write equals brace init list, that's copy list initialization. If you pass in a brace init list or return a brace init list, that's the same. Passing and returning brace init lists is kind of interesting because then it tries to, you didn't write the types, it's going to match this brace init list thing against different things. And there's all kinds of different cases. So there was this delightful example on Stack Overflow a couple months ago where you pass in a brace init list depending on how many levels of nested braces you have. You're going to get very different results. So we don't have time to discuss this in detail. It's fascinating. You can work out what happens, but it's really interesting. So list initialization has a few problems. Right, so I need to go very quickly over this. C++ 14 just fixed a few things, like in C++ 11, aggregates were not allowed to have direct member initializers, which was very unfortunate. Surprised a lot of people. Since C++ 14, that's fine. Another fix in C++ 14 was auto and list initialization. So in C++ 11, if you had, so it's kind of weird because if you have an integer and you replace that integer by auto, which is good practice, you should use auto always, then you get different results all of a sudden. So if you have brace, it's always going to be an initializer list. And then if you write auto I like 3, you probably wanted to say it's an int. So in C++ 14, that was fixed. So now if you have just braces with auto, that's going to do basically direct initialization. If you have like an integer or float or a bool, like a built-in type, and if it's more than one initializer, that you can't do that. And then if you have equals brace, then it's going to be an initializer list. So now the auto brace thing is not consistent with itself really because like equals means something else than not equals, but at least it's more consistent with not having an auto. So it's a bit better than in C++ 11. And then the other problem with list init is that you can't use it in macros at all, right? So assert, for example, is a macro. If you use direct initialization there with parens, there's a special parsing rule for parsing in the preprocessor that if you have a comma in there inside parens, that's fine. If you have braces, there is no such special rule. So if you have a comma inside the brace init list, inside a macro, it's going to think, oh, well, the comma, that's the first macro argument. And it's going to start parsing like another macro argument from inside the brace init list. And then the parser will just break and say, syntax error, doesn't work. So, recommendations. And this is kind of my personal coding style. I know that other people have a different opinion on this. I personally like to use copy initialization for simple value types like integer and float and so on and so forth. Because that's just a syntax that is very intuitive. It exists in pretty much almost every other programming language. You know, int I equals 3. That, everyone understands that very quickly. It's less confusing than using something else, in my opinion. I use list initialization for those things where they're really, really useful. Like, for example, aggregate initialization. This is where, you know, you cannot do it without braces in C++ 17. So this is what I use braces for. If I want to do aggregate initialization, I use braces. The other thing is if I want to call a std initializer list, like for a vector, for example, then I also use braces because this is the only way I can do this. And the third case is if I have a direct member initializer and takes multiple arguments, I cannot use the paren syntax there because that's not allowed for, I'm not exactly sure why. So then you have to use braces there as well. And then the other thing that I find really useful is the syntax where you just return temporary functions or you pass in temporary functions. Like for example, if you have something like a point, which just has, you know, two elements, and then you can create these points on the fly like this, and you don't even have to write the type, right? You can just write brace 2, 3. So as you saw in the earlier slide, sometimes it becomes more complicated, but this is like a case where it's really obvious what's going on, so it's just less code to write. So I think that's good practice. And then my last recommendation, which is the controversial one, which is if I want to just call constructors, I use parens. And I know that other people like Nico Yusutis say you should use braces for that. I don't like braces because they don't work in templates. They do sometimes weird conversions. And if I use parens, I know it's just going to do overload resolution. So I can tell it, okay, I want to use initializer list, then I write brace, or I don't want to use initializer list, then, you know, I use parens, and then it's just going to be normal overload resolution, easy. You know, everyone knows how that works. So I think this is easier to use. Of course, parens have the problem with the vexing parse, but there's a solution for that. So you can use auto. So there is this, a while ago, Herb Sutter wrote this very influential article about almost always auto, which means you should just use it like this. And the interesting thing is that if you just use auto like this, then actually the vexing parse problem goes away. Right? So this, if you write thingy, paren, paren, that's going to declare a function. If you do the same, but just write the thing on the right-hand side and use auto, then you get rid of the vexing parse problem. Okay, don't have time to talk about that. So we fixed this in C++ 14, where basically using this auto syntax used to require that you have a copy or move constructor, even though it's not going to call it, it's just going to initialize the thing. That's fixed in C++ 17. We now have what's called guaranteed copy elision, so that's fine even for a type like atomic, which is not copyable, not movable. So you're guaranteed that writing auto count equals atomic 0 is exactly the same as writing atomic count equals 0. The only case where you cannot use auto, again, is direct member initializers. They're a bit special, so you cannot declare members using auto. And then there's this other thing, which is CTAD, which also has weird interactions with initializer lists sometimes, which I don't have time to go into either, but I do have a whole 1-hour talk just about CTAD. So if you want to know about that, watch this one. Okay, so this is where we are in C++ 17. I have a few more slides about what's going to be new in C++ 20, but I think we ran out of time. So I need to skip that, unfortunately. And what? How many? Yeah? How many? Do we have a few more minutes? How long? Okay, very, very quickly. So in C++ 20, we're going to get a new way of initializing things, which is designated initializers, which is this thing that we used to have in C since C99, which is where it's a way of aggregate initializing things. But instead of doing it in order and leaving out elements at the end if you want, you can actually name the members. So you can, for example, if you have A, B, and C, you can say A equals this, C equals that, and skip the B, and then the B is going to be 0 initialized. So it's a more flexible way of doing aggregate initialization, and it's been in C since C99, and now we're going to get it in C++ as well since C++ 20. There's a few details where C++ 20 will be slightly different from C. It's going to be some things that you can do in C, you will not be able to do in C++. You cannot change the order, because in C++ initialization order actually matters. As members are initialized in order of declaration and destroyed in the reverse order of declaration. You can't nest these things. You can't mix designated and regular initializers, because why would you want to do that? And it doesn't work with arrays as well. Another change is like a slight fix for the rules for aggregates. So this is a paper that I wrote where basically in C++ 17 we have this problem that aggregate initialization sometimes behaves in weird ways. Like if you have a deleted default constructor, then you can't call it. But if you do brace brace, it's going to instead do aggregate initialization. That surprises a lot of people. So typically when you write equals delete, it means you cannot default initialize this, or you cannot instantiate this thing at all. But then if you just write brace brace, you can kind of circumvent that and do aggregate initialization instead. So in C++ 20, we changed the rules and say, as soon as you declare any constructor, it's not an aggregate anymore. So you cannot have weird clashes between constructors and aggregate initialization. It's much simpler now. And the other thing is just a minor fix. In C++ 17, array size deduction doesn't work with brace init lists, which is just an oversight. When brace init lists were introduced, they didn't add the special case for array size deduction in new expressions. So we fixed that. And then there's one more thing which I'm really excited about. So we saw that list init has these problems, and some of them are specifically very unfortunate because they also affect aggregate initialization, which is like the easier thing, not the one with the std initializer list. So you have aggregates, but you can't use them in templates, so you can't write an in-place or a make unique function or like perfect forwarding kind of function that works for aggregates, because you can't really use braces the way you use them normally inside these kind of functions. And the other problem is that it does not work with macros. And in C++ 20, we're going to fix both of these problems. And that's this paper, P0960, which says, well, in C++ 20, you can just use parens to do aggregate initialization. And that will just work. And same with, so of course, you should use auto, but then this also works with arrays. So aggregate initialization for both arrays and aggregate classes will just work with parens. And that's really nice, I think, because then in C++20, basically parens and curlies mean the same thing most of the time. Except parens cannot call std initializer list constructors, and curlies do not allow narrowing conversions. So these are pretty much the two only differences. Yeah, so that's what we're going to get in 20. I think that's going to, again, simplify everything. Because then you can just use parens most of the time, except if you want initializer list constructors, then you can use curlies. Yep, and again, the recommendations, it's just repeating what I said earlier. And then the last slide is this overview table over everything we've discussed. So the rows are the different kinds of types, and the columns are the different syntaxes, and this table tells you what they do. You don't have to take a picture of this, because if you find me on Twitter, I just pinned that picture to my profile so you can get it from there. And that's it. That's all I have. Thank you.